Okay, so as long as we satisfy our hypotheses, if our improper integral diverges, then our series is going to diverge. Let's look at some examples. If we consider functions f of x equals 1 over x to the p for p greater than 0, these are continuous, positive, and decreasing as long as we're looking at x values greater than or equal to 1. Right? We can push that out a little bit, but they're definitely continuous, positive, and decreasing for x greater than or equal to 1. We know that if we look at the integral from 1 to x, 1 to infinity, that this diverges. So that implies that the harmonic series also diverges. And in fact, if we think back to what the condition was for divergence of the improper integral, or we could recheck it, we said that if 0 was less than p, was less than or equal to 1, then this integral from 1 to infinity of 1 over x dx is going to diverge. 1 over x to the p dx is going to diverge. What that means for us is that as long as p is between 0 and 1, then this series from n equals 1 to infinity of 1 over n to the p is going to diverge. All right, let's look at some values of p. So this means, in particular, if we have p equal to 1/2, then the series n equals 1 to infinity 1 over the square root of n is going to diverge. So we're going to get an infinite sum. If we look at p is equal to 0.99, then 1 plus 1 over 2 to the 0.99 plus 1 over 3 to the 0.99, and so on, is going to diverge. Okay, because we have this value of p, these are called p series. So anything that has this form, n equals 1 to infinity, 1 over n to the p, is called a p series. And we've just discovered that if 0 is less than p is less than or equal to 1, the series diverges. Okay, next we're going to consider convergence of series that come from continuous positive decreasing functions. In this problem, we want to show that the series from n equals 1 to infinity of log n over n diverges. If we check the divergence test and look at the limit of the values log n over n, well, we have a logarithm over a polynomial. You're free to use L'Hopital's rule, but you'll see pretty quickly that this has a limit of 0, right? Because this has the form infinity over infinity, so when we do L'Hopital's rule, we get 1 over x divided by 1 and we get a limit of 0. So it's inconclusive. Okay. Divergence test, though, is something that's easy to do, so it's a great starting place whenever you see an unfamiliar series. Okay, but when we look at this, we think we can integrate. We can calculate the integral of log x over x. This makes it a good candidate for the integral test. The integral test is only helpful if you're going to be able to calculate this kind of integral. Okay, so since we can integrate it, we might think about the integral test. So next we need to check our hypotheses. Okay, so the 3 hypotheses that we need to check is that our function is positive eventually. That's pretty clear. I hope you can see that if x is greater than 1, then we are positive, because log x is positive and x is positive. We are continuous for x greater than 1. Decreasing, to show decreasing, we need to do a little bit more work. A good strategy for showing that a function is decreasing is to calculate the derivative and show that it is negative, right? Because that implies that our function is decreasing. All right, so let's calculate this derivative. We're going to use the quotient rule. So we get 1 over x times x minus log of x over x squared. So this is 1 minus log of x over x squared. This is negative when 1 minus log of x is negative, which happens when log of x is greater than 1. Which is when x is greater than e. Okay, so eventually, when x is greater than e, this function is in fact decreasing. So I'm going to give it a check mark. Excellent. As in all sort of series tests, as long as something holds eventually, it's good enough. Okay, so let's take a look. Let's try and integrate log x over x. And we're going to be looking at it from 1 to infinity. Okay, so I'm going to start by just calculating log x over x. Let's just find what the antiderivative is, and then we'll take the limits. Okay, so we're going to do a u substitution with u equal to log of x. Then du is 1 over x dx. Okay, so my integral is equal to the integral of u du, which integrates to u squared over 2, or log x squared over 2. Okay, so my integral from 1 to infinity of log x over x dx is equal to the limit as b goes to infinity of log b squared over 2 minus log of 1 squared over 2. Right, I'm just evaluating the difference of my antiderivatives evaluated at the limits of integration, and we find that this is equal to infinity. Right, as b goes to infinity, log of b goes to infinity, and we're only making these terms bigger by squaring them. Okay, so the improper integral diverges. And hence my series diverges. Since we know that the improper integral is a lower bound for the sum of this series. Okay, now let's talk about convergence.